Hello, everyone. I'm Illyoung Choi. I'm a PhD student at University of Arizona. I did a summer intern at ONF this year, so I had a chance to do a research on a workflow management engine in Cord. This talk is to present the research and to talk about the requirements of future workflow management engine. A workflow is a program that consists of a series of tasks and runs repeatedly for a repeatable goal. It is like do X, Y, and Z at a particular event. Each task is a small step to achieve a big goal of a workflow. So each task defines when to execute the task and what is the goal of the task and how to achieve it. So each is represented as event, action, and result. Current workflows in Cord are implemented as XOS synchronizers. XOS synchronizer defines data using data models and actions using model policies and event steps. Model policies are event handlers for model update events. Event steps are event handlers for events that are raised by other services in Cord, such as ONF. A figure on the right describes design of AT&T workflow. The workflow is for optical network unit boot-up process. The workflow consists of multiple event steps that detect particular events and do some tasks. The pink one are the event steps. And they read and write to a data model to manage workflow's internal data. That is green one. Updates made on the data model triggers a model policy. That is the blue one. And the model policy can do some actions like making some other updates on Cord data models. This is to change the state of the system. For example, a DHCP event comes, then the DHCP event step checks the data model for the ONU device is properly authenticated, and then it updates the data model for moving the state of the workflow. And then this triggers the model policy, and then the model policy updates the Cord data models to propagate the changes. That is kind of, for example, the change is the ONU device is assigned with an IP address as a result of DHCP. There are some difficulties and limitations in current XOS synchronizer-based workflow implementation. In development, there are two different types of event handlers providing inconsistent interfaces with different technologies involved. Also, a workflow implementation consists of multiple event handlers that are seemingly fragmented. There's no direct relation stated between the event handlers, so they look independent at a first glance. The state of workflow is managed manually, so programmers should implement a state machine on top of seemingly fragmented event handlers. So that's manual process. And this makes a system can track the status of workflow. And there can be a possible race conditions and loops. I will show you an example of these. at the next slide. And it is difficult to understand execution flows of workflow and finding relations between multiple workflows in a system. And it is also difficult to monitor workflow state. Back to the AT&T workflow example, its execution flow at the first glance will be like this, because the source code are fragmented and there's no direct relation stated in the code. So at the first glance, we can only understand that there are these components, but no relations. You have to put a lot of efforts to understand the code in order to figure out these hidden paths. So this is really time-taking step. So if a workflow is more complicated, then you will need more time and more effort to discover all execution paths. In XOS synchronizer, events are handled differently according to their types. External events are handled by event steps, whereas model events are handled by model policies. They not only have different interfaces here, but also behaves differently. Event steps are implemented with Kafka message bus. When an event is raised by external services like ONF, the event is sent to Kafka and buffered. Later, the event step detects the events. On the other hand, model policies are implemented with gRPC with polling. Therefore, updates made on a data model are accumulated and detected in the next cycle. So this does not guarantee that every update made on a data set raises an event. So this can make programmers confused. It is also possible that a workflow can cause race conditions here or loops. But it is difficult to find these possible race conditions or loops between multiple workflows in a system without clear understanding of their relationship. So to address these difficulties and limitations of synchronizer-based workflow implementation, I developed a proof of concept workflow management engine. The pilot engine is based on Apache Airflow, which is an open source workflow engine developed by Airbnb. I chose Apache Airflow because it is the most widely used one. The pilot engine offered simple and consistent interfaces for event handling, and it enforces stating the execution flow clearly, and it automatically manages states of workflow, and it provides some tools for tools to avoid race conditions, and it also visualizes workflows as graphs, so you can easily find loops or possible race conditions. And it also helps figuring out the relationships between workflows or figuring out execution flow of a workflow. And it is also scalable using external libraries like Kubernetes or Celery framework. The design of pilot engine is like this. It consists of three main components. probes are responsible for detecting events and send events to workflow controller. And the controller is the core part. It routes events to workflows run on Airflow. Airflow extension provides interfaces to workflows to communicate with workflow controller. Basically, cold workflows are online transactional processing, whereas Airflow is designed for online analytical processing. The online transactional processing is a type of short and fast transactional workloads. But online analytical processing is a type of periodical batch workloads. So OLAP is more less time sensitive than OLTP. So workflow controller has to manage the transaction needed by code, but we need to solve that problem using Airflow that is OLAP basis. So the workflow controller bridges the gap between the two. The workflow controller manages workflow instances life cycle, and it launches, for example, it launches new instances of workflows and monitors its state. That is to route events properly, actually. So its main goal is routing events to workflow instances properly so that Airflow can handle the events and run workflow instances smoothly. Using the pilot engine, workflow code becomes clear. The pilot engine provides three components: sensors for when, and operators for how, and data models for what. And it enforces explicit flow definition between tasks, as shown in the right bottom corner. Using these, workflow implementation becomes clear, so they're easy to follow the execution flow. Both humans and machines can easily understand the connection between the tasks and connection between the workflows in a system. So that's the benefit. Using the pilot engine, the AT&T workflow design also gets changed. So comparing to XOS synchronizer-based workflow design, a workflow design using the pilot engine has a clear execution flow. For example, XOS synchronizer has 4 entry points, as you've seen above, 3 pings and 1 admin UI. These entry points look independent to each other. Therefore, any of them can start the workflow. However, the AT&T workflow in reality has a certain event order. For example, the ONU has to be the first one, and then auth can come next, and DHCP is the last one. So developers has to manually implement a state machine to ensure this order. On the other hand, the pilot engine automatically enforces this order because the workflow is designed like that. And when you first, at your first glance of the source code, with the XOS synchronizer based implementation, you can only understand this blurry, looking seemingly fragmented code pieces and no relations. But with the pilot engine, you can easily figure out all the execution flows because they are stated in a fixed location with just few lines of um, um, statement about the relations. The pilot engine also provides nice monitoring UIs that are provided by Airflow. Um, this shows how many instances are running for each workflows and how many are currently running and how many were succeeded and how many were failed. And it also shows different presentation of a workflow, and it also shows how they are look like and what is the state of the workflow. The pilot engine also has some limitations. These limitations are mainly caused by Airflow. Airflow basically uses polling to detect events, and Airflow recommends to use long interval, like a few seconds. Because of this, it cannot immediately detect events when they are raised. Also, it takes pretty long time, like a few seconds, for scheduling a new task. Also, Airflow's task scheduler is a single point of failure, although it provides scalability to workflow execution. And its web UI is not scalable to display thousands of workflow instances. It also has annoying workflow registrations. Sometimes it cannot detect new workflows, so you need to restart the workflow, Airflow. And it also has some programming restriction, like all the workflow, each workflow should be in a single Python file. And these start points are related to the Airflow design that is mainly designed for OLAP. So that's reasonable in the view of Airflow system, but that's not good for core system. So I think based on these research results of the pilot engine, I think future workflow management engine in core should have these features. I want to provide simple and consistent event handlers as we've seen in the pilot engine. And we want simple automatic state management and flow control and fast and easy task scheduling and automatic loop detection and avoid race conditions and visualizations for monitorings and fast event detection, fast task scheduling, high availabilities. These features, some of these features are already implemented using in the pilot engine, but many of them are not implemented because Airflow couldn't support that features. And then the Airflow basically distributes tasks over a cluster. That is their main idea of providing scalability. But XOS synchronizer distributes workflow level granularity to distribute their tasks over a cluster. But I think XOS synchronizer's approach is better than Airflow's approach because Airflow took more time in scheduling the task because they need to manage everything for every task. So if we have a lot of tasks, then it will take more time. But XOS synchronizer distributes a workflow-based basis, so it takes less time in switching tasks in a workflow. So XOS synchronizer and the pilot engine have different advantages. XOS synchronizer have a good separation of concerns, so they only need to focus on their jobs when they need to, when programmers develop a workflow. But pilot engine, once everything is connected and everything should be monitored automatically and they are connected, so we want centralized view of those workflows and tasks in a workflow. So that should be explicit. So they have different advantages in design. So the future workflow engine should have balanced point of those two advantages. Yeah, that's it. Do you have any question about the presentation? Here, basically, there are two execution paths in current AT&T workflow. One is instantiated by the system, like when ONU event when ONU event comes, then the blue path starts. And the other one is administrators can forcefully update data model, this one, using XOS Web UI. In that case, that is, for example, the administrator wants to disable ONU device forcefully or enable. So there are two execution passes. And then in pilot engine, we want to break down those two because they are separated, conceptually separated.
So the answer is two.
Yeah.
Is that right? So what is the thing on the right-hand side, the ARC cord service? It's not a workflow from Airflow's point of view?
That's not the part of AT&T workflow, actually. That's the part of cord system.
I see.
Yeah. That's kind of other internal workflows.
Okay. And also then that big one, you don't think of that as three workflows. You think of that as one multi-part workflow. It literally is written that way.
Yeah.
Okay, thanks. Other questions?
Yeah. Just thinking out loud, is there a need from an operator's perspective to create workflows on the fly, right? For example, I'm an operator, I want to make a change to a workflow or create a new workflow. I don't need to program it. Is there a design time aspects to these synchronizer or things we're looking at?
I wasn't able to understand the letter.
I guess the key question is there a on-the-fly design perhaps tool that XOS needs to look at or synchronizer need to support because that might be beneficial to the community?
This is the kind of figuring out a better design that can possibly replace existing XOS synchronizer. So because XOS synchronizer has limitations and difficulties, so we want a better system that can provide better programming and monitoring environment.
Could you try to rephrase? Could you imagine a value in creating workflows on the fly? As an operator.
What do you mean by on the fly?
As an operator, you suddenly discover that you're under attack.
Mm-hmm.
And you need, whenever this event happens, I really want to do this other thing that I hadn't thought of yesterday.
Mm-hmm.
Is that outside of the scope or?
No, actually that was the part here, the workflow registration, that should be done in runtime using this new system, because we may want to introduce new workflow without restarting or without redeploying the system. So that should be done in runtime. And then the reason we want to provide the packaging of workflow, workflow code packaging tools or runtime registration things are all for the dynamic deploying of the service. Yeah, that's related actually. Yeah.
Thank you.
Thank you.